Shall we start? Okay. So let's finish this long proof that always, yeah, remember what we are trying to prove. We just want to show that so we want to show that for some reason the pen has become very thin. So let me just this is better. Yeah. So we had this x dot equal to f of x.
You have not shared the screen, I think.
Oh, sorry. Yeah. Yeah. So x of 0 equal to y. The solution we call u of x comma y, u of t comma y, and we want to show that u is c1 as a function of both variables. And so this was the main thing that we had last time. We had if, and we had guessed a derivative, a candidate for the partial derivatives of u with respect to the y variables. That was the fundamental matrix. So let's see, right? Yeah. So if g of t equal to norm of u t y naught. So we are proving differentiability at a point y naught minus u t y naught plus h plus that fundamental matrix, which is the candidate p t y naught h. Then we had last time we had this g of t less than or equal to m1 0 to t g of s ds plus epsilon naught norm h e to the power k a. This was what we had here. The only new thing k was the Lipschitz constant as before, and a was the interval of solution. And the only new thing was this m1. M1 was a bound, upper bound for the norm of the derivative of f. Now I omitted something here in that calculation last time. I said that I would do that. So let's see what part where m1 made an appearance. Oh my God, this has become very small. I don't know how the font has changed. Oh no, not the font. I mean the pen thickness has decreased in something that I have already written before. But so Yeah. So notice that the quantity we are trying to estimate had two things. One was there was an integral involving the derivative of f and some stuff inside brackets which I called g of t actually. Here it's g of s. Now in the first that integral I said is less than or equal to m1 times g of s ds. Now, so what does this? So essentially, I have something like the picture is this. This is a linear transformation here. This entire thing in the brackets is a vector. So I have a linear transformation A times a vector, and I'm taking the norm. I would like to say this is less than or equal to norm A times norm B. Which and then which would make sense provided we have an appropriate notion of norm of a linear transformation. See this V and AV are just vectors, column vectors. So we can use the Euclidean norm, the Pythagorean norm on this. It's only this, which is a matrix or a linear transformation. What? How do we talk about? By the way, now that I've increased the size of this pen, when I hover over the screen, I see a huge dot. Do you see this?
Yes, sir, we see it too.
Oh, this is actually better. Yeah, okay. So, how do we make sense of this norm A? Well, there are a couple of ways. One is A is a matrix. If you think of A as a matrix, in this case, it would be an n by n matrix, but the size is not important. You can still take the Euclidean norm of that. In other words, you just square the entries, add them all up, and then take the square root. That gives a perfectly valid norm. Implicitly, you're just identifying the matrix with a Euclidean space of the appropriate dimension, n times n, if the size of the matrix is n by m. So that's okay, but that won't give this inequality though, if we do that. Rather, the right definition for the norm of a linear transformation is something which will work not only for finite dimensional vector spaces, but for all vector spaces. And that is this operator norm. So here, norm of A is by definition sup norm AV, and you take the sup over all vectors with length less than or equal to 1. So in other words, the unit ball, closed unit ball, you take the sup, and this gives a valid norm one can check. So I'll leave it to you to check that this is a norm on the vector space of linear transformations from Rn to, actually it can be any dimensions. As I said, it even works if you don't even need finite dimensional vector spaces. You know that the set of linear transformations from one vector space to another is itself a vector space. On that vector space, this is a norm. And you can also check that the way the norm is defined, it's almost immediate that we have this. This is the main property of this operator norm. Simply because, well, here this is supposed to hold for all V. You have to do is you just divide both
Take a
sides.
unit vector.
Yeah, that's all.
Take
Just
a unit vector.
take a unit vector or just divide both sides by norm V. So then A will be acting on the unit vector V divided by norm V. And by definition, since the operator norm is the soup of all such these things, so you'll get A acting on V by norm V less than or equal to, norm of that is less than or equal to operator norm of A. So it's almost designed to make that inequality work. So here when I say M1, now we wanted to apply it at this stage here. So M1 is the operator norm of this thing here, this linear transformation. M1 equal to operator norm of, rather the soup of all those operator norms over oops. Yeah, it is in then oh my god, what happened to this? M1 yeah. Right. M1, oops, again it went back to the horrible. Let's see, where was that? Let's see. M1 equal to soup operator norm of DF of US by naught. And what is the soup taken over? Well, actually, no, forget US why not. It's, let me just put DF, let's say X, where X is in this, we are working inside some small ball, right? I think n delta or n delta by 2, one of these two will do. N delta, why not? That's it. So you, anyway, F is C1. So all its derivatives are all, partial derivatives are all continuous. So, and the norm of a continuous function is a continuous. So this will be on this set, it will be bounded. Again, just have to take the closure of this set and then use compactness to say it's bounded. That's it. But what I wanted to emphasize was that when I say norm of that, it's the operator norm. And then once you have M1 as a soup over all such things, then it's each operator norm will be less than or equal to M1. I mean, at each point it will be less than or equal to M1. So therefore, inside the integral, you can use this inequality here, and you get out M1, take out M1. So that's that. Well, this is again of the form. This is again of a form where I can apply Grunwald's inequality. So let's do that. Grunwald. Note that this is the second time we are doing this. Grunwald implies g of t less than or equal to. Well, this is the constant, so I'll just put it in here, less than or equal to this thing here. And then this m1 will play the role of the exponent now. E m1 t. So how has all this helped us? Well, ultimately at the end of the day, so we wanted to see that yeah, again I replace by yeah, so which is less than or equal to t is anyway going to be less than or equal to e to the ka e to the m1 a. So I do that. So remember that our goal was to somehow we were interested in showing that g of t divided by norm h limit h going to 0, this should be 0. But what we have shown is pretty much that, because what we have shown is this less than or equal to, after I divide by norm h, epsilon naught. This remaining stuff is anyway, it's just a fixed constant. It doesn't depend on h. So epsilon naught was arbitrary. So given any epsilon naught, we found that. So actually, what was the restriction on h? We should need a restriction. We can't get it for any h, right? So where did we use the restriction? So and where did see here? Given epsilon naught greater than 0, there exists delta such that if this. So basically, we used it in the estimating the remainder term here. So the remainder term had to be of a certain form. And then we were able to finally get that this less than or equal to epsilon naught times some constant. So therefore, limit g of t divided by norm h, h going to 0 is equal to 0. Okay, so I also say that h, right, h should also be, yeah, by the way, a note that I put here earlier on, I put h less than delta naught. That delta naught was coming from estimating the remainder term, but even before that, we need to say that h is less than delta by 2 for a very trivial reason, just to ensure that, see, this y naught was there, even, and there's y naught plus h. So I want to ensure that I stay within the delta by 2 ball around y naught. So that's why I put h less than delta by 2. Okay, so this is the first obvious thing. The other thing is that other delta naught comes from the remainder term calculation. So at any rate, after making h small, we can ensure that g of t by norm h is less than epsilon naught, and therefore, so this shows, therefore, this precisely implies that what Perco refers to as del u by del y at ty naught is equal to phi, the fundamental solution. So this notation, when Perco writes del u by del y, you should be a bit careful because y is not a single real variable. Y is actually n variables. So what he means is this is shorthand notation for just our du. If you fix t, u becomes a function from Rn to Rn, or rather u to Rn, and then this is du py naught. So this is within quotation marks. So this equal to this. In short, u has been shown to be differentiable with, of course, it's already differentiable with respect to t. It's also differentiable with respect to y. And in fact, its derivative is this fundamental matrix solution phi, which we know is definitely going to be continuous. In fact, it's differentiable. So we are done. Okay. Now, fortunately, before I proceed further, let me tell you the homework for this section. I already told you one of them, problem 3. So page 85, 2, 3, and 4. 4 is, as it turns out, page 85. 3 rather. 3 is something which is not really, I mean, it's a refinement of what I'm going to say. Let me put it like that. It's basically a question about dependence on parameters. One can get a nice statement about how the solution depends on parameters in a second, but this 3 is even stronger statement. You don't need to assume so much about the function f. So dependence on parameters. Surprisingly, perhaps not so surprising, if you see how it works out. So as I said, we would like to see, so we are in this same old problem. We want to see how the solution is going to change when we are allowed to move the initial condition slightly, change it slightly, as well as changing the function itself. So for instance, suppose I have the equation x dot equal to x square, x of 0 equal to y. What do I mean by changing the function slightly? I can consider, for instance, x dot equal to x squared plus epsilon x. For each epsilon, I get a differential equation. Epsilon equal to 0 would correspond to the original equation. So what one would expect is, if the initial conditions are, I mean, same or close, then the solutions to the new equation should be close to the solutions to the old equation. In other words, continuous dependence on this. The solution should depend continuously on epsilon. So, and in fact, that turns out to be the case. Well, continuous or more. I just said continuous. Maybe one would even have stronger dependence, like it should vary differentiably with respect to epsilon and so on. So let's see. So here the parameter, but there is a choice involved here. The parameter, for instance, here is just 1. But I can make any number of parameters actually. So even in this single equation, for instance, I can take x dot equal to x square plus epsilon x epsilon 1 plus epsilon 2 x cubed, whatever I want. So now I have 2 parameters. So Perko considers the case when the parameters where they can change within another Euclidean space are M. And so let's see what the so let us take U to be an open subset of Rn plus M. And F from C1U back to Rn, x naught a point in, rather x naught mu naught a point in Rn. Rn plus M, I'm thinking of identifying with Rn cross Rm. So it's a pair, x naught mu naught in Rn plus M. So, right. Yeah, the point is now the point is that I have a function of 2 variables, x and mu. For instance, here it would be f of x epsilon 1 epsilon 2. And then so here's the theorem now. So theorem with this setup, there exists a greater than 0, delta greater than 0, such that for all y, so I'm allowing the parameters, the initial condition to vary as well, n delta x naught mu n delta mu naught, oops, not x naught again, mu naught the equation, the system f of x mu x0 equal to y is a unique solution. By the way, another thing which you should note here is that that is also actually quite important, which is that when we vary all this stuff, there's always a fear that the intervals of definition might shrink. But one of the conclusions, even though it's not explicit, it's implicit in this, is that as long as y doesn't vary wander too far away from yeah, as long as y doesn't wander too far away from x naught, similarly mu doesn't change too much from mu naught, the same A is going to work for all the solutions. So all the solutions here, starting at different initial values and for different functions, they will continue to be defined on the same interval A. There's a unique solution U, T, Y, mu, and this U is going to be a C1 function on G Rn. G now is a minus A to A cross n delta x naught cross n delta u naught. So the point is that for all these values of initial values and for all parameter values, the same interval here will will work. The solution is defined on the same interval. It doesn't shrink.
Excuse me, sir.
Yeah.
So essentially, you are saying that there are two variants. In case one, we get a mu and then we give an interval. In case two, we give an interval first, which works for all mu. So you're saying case two, which is a stronger case, is going to be the statement of this theorem.
Well, there's no question of case one. I mean, the thing is that it's forget for example we have introduced mu as the new parameter. Forget mu. Let's just think of, for simplicity, about dependence on initial conditions. What we discussed last time. Just this.
Can we think like this? Like we get a ball in x naught mu naught that Rm cross n dimension, and then we enclose it in a smaller rectangle or a smaller cross product of balls.
Not enclose it, it should contain.
Yes, contain. Sorry. Yeah, it should be inside that.
Well, yeah, that's right. Yeah, that's in fact, it's part of the process that drops out automatically. That the same interval will work for the moment you are able to get an open set around say x naught and 0, the point containing 0 and x naught. If you find any open set on which the solution is guaranteed to exist, but actually there is even to make a statement about solutions, there is a slight issue here. Even to make a statement about solutions, you have to already have something like this. The region on which you are talking about a solution should already be of a product domain type of thing. Otherwise, it doesn't, even to define what it means, becomes a tricky thing. I mean, how do you say there is a solution on a ball? Let's say here ball would be inside R cross Rn. Forget mu for a second. This is the T parameter. This is the Y parameter. If I take an open set here, what do I mean when I say that this and a function on and a mapping into that? What instead of G? Yeah, instead of G. Yeah.
I was trying to say, like, from the previous theorem, we get a delta ball in R n cross m of x naught comma mu naught, right?
Oh, you're saying no, you're talking about a different issue. You're talking about how this parameter dependence can be reduced to the earlier case, is it?
Yes.
Well, that is true. In fact, that's a quick proof. But anyway, I was talking about something else, that even in the earlier case, forget this mu. Even in the case of just dependence on initial conditions, the fact that in order to make all these statements, smooth dependence or even continuity, you have to first show that the same A will work for all solutions if you're close enough to a given solution, close enough to x naught. That is a starting point. But that is anyway part of the theorem. You don't have to prove anything extra. All this has been hidden in the theorem, but I just wanted to point it out. That's all. Now, coming to the case of parameters, as you said, I don't know if this is what you had in mind, but the point is that this theorem actually you don't need a separate proof, as it turns out. It reduces to the previous one. In fact, if you fix the initial condition, it just reduces to the original proof of Picard's theorem. Because why? Well, just the way this itself suggests something, the fact that f is a function from Rn cross Rm into Rn. So what you do is define, replace x by x mu, then of course that immediately implies by x naught by x naught mu naught x dot by x dot 0 and y by y mu in the previous theorem. In other words, what are we more formally? What are we doing? Well, we are introducing more variables and functions. That's all. See, in the original setup, we had this. Earlier we had this. Now we have this. But well, why not think of x mu itself as a f is anyway a function of x comma mu. So instead of thinking x as the variable of f, you regard it as x comma mu. But then question has to be formulated. Remember, in the systems we are dealing with, f is always going to be from Euclidean space back to itself, Rn to Rn. So here, what I'm saying is replace x by, so z equal to x mu. But instead of f, even in this modified setup, f is landing back inside Rn itself, right? So I want to get a new f. So let's call it f1 of z. I want it landed in Rm. So I want f1 to go to f1 from Rn plus m back to Rn plus m. So the first component, so it should have two components. The first component is clear. It should be this f of z. What should the second component be? Well, let's guess. After all, f is related to the differential equation. Ultimately, I want to get something like z dot equal to f1z and apply the previous thing. So if I want this, then z dot would be x dot. Now this mu should not depend on t. It is it's nothing to do with the solution. It's a parameter. So x is the thing which the solution is, plays a role. So here it should be 0. This should be f1 of z. So that means which is f of z something, but that something should be 0. That's all. Because it's 0 here. And what about y? Well, y is again, I mean, y is just a parameter. Y is a point in Rn plus m. So it will be again of the form y comma mu. So in terms of z, z of 0 should be, what is this? Z was x comma mu. X of 0, which is y comma mu. That's it. So this is the new initial condition, y comma mu instead of y. Replace y by this. So you have what you have done is, by doing all this, you have now have a new problem. For f1 and z of 0 is y comma mu. So you just go back to the previous theorem and claim that the solution will depend smoothly on y comma mu. That's yeah, well, that's it. Now, in the, as I said, in the homework problem exercise, he again proves the same thing, except that notice that here, what is the assumption is, the starting assumption is that f, where was I? Yeah, f is right here, in fact. F depends smoothly on both x and mu. That was the standing assumption here. The theorem was proved under that assumption. And the conclusion is the solution depends smoothly on everything. But what the homework problem tells you is that, let's see, so yeah, homework problem tells you that this f yeah, well, the homework problem is actually, the conclusion is also weaker. It's you won't get that the solution depends smoothly on mu. You only get continuous. So basically, it's a slightly different thing. You make weaker assumption on f, and you get a weaker assumption on u. So, but that has to be proved separately. If you have the stronger assumptions like we did, then you can reduce it to the previous theorem and get a stronger conclusion as well. So it's a trade-off. But unfortunately, the same proof, you can't use the, you can't code the previous theorem to do the homework problem. You have to do the all the steps again. So I hope this is clear what I did. This is one of those tricks, just like we reduced inhomogeneous to homogeneous or second order to first order. It's along the same vein. Now, given,
Sir,
yeah, right.
sir, our initial claim was yeah, the solution is C1 on
Yeah,
A cross A multiplied by n delta by 2x naught. We
yeah,
proved that it is we proved that the derivative exists, but first
yeah,
question is how do we know it is continuous? And second question is if we know that okay after fixing t the total derivative exists, how do we know
yeah.
that all of the I mean without fixing t also the total derivative exists?
Without fixing t. No, we don't
Yes.
know. See, yeah, no, we don't. See, in the previous one, to answer your first question, say you wanted to say that u is C1 in as a function of t and y. So what does C1 as a I mentioned this in the last class, actually beginning of last class, that what does this mean really? It means del u by del t, del u by del y1, etc., del u by del yn. All of these exist and are continuous. So del u by del t is exists and is continuous, follows from the differential equation. After all, del u by del t is f of u, which is more than continuous as a function of t. Now, what about this other? The more interesting thing is del u by del y1, etc. What this calculation tells you is that these are all column vector, right? This del u by del y1 is actually a vector because u itself has components, right? u1, u2, un. So these column vectors del u by del y are what make up this matrix here. So, but what we are saying is that these column vectors are the same as the column vectors of this fundamental matrix. Again, the fundamental matrix is by definition, actually I did the whole thing last time, is comprised of solutions to a linear system, of a different linear system. Therefore, they are all the columns of this are not only continuous, but they are actually differentiable. So the columns of this are also continuous or differentiable. Therefore, all these things are certainly continuous. So therefore, U is C1. That's the argument. Okay.
Yes, sir.
Um, all right. So yeah, actually, in fact, when we prove that this thing, it's not just differentiability we are showing of u with respect to y, but we have explicitly calculated what the derivative is. Explicitly in some sense, but explicit enough to say that derivatives are all continuous because this phi is definitely continuous, more than continuous. So we have done in great detail the proof of dependence on initial conditions and parameters. Now we move on to another very important topic. All these things, if you study any area of mathematics where ODEs are used, for example, in Riemannian geometry, one talks about existence of geodesics and all that. Or even when you have a vector field, you have integral curves and so on. You'll see all this, whatever we have proved, being literally used as they are. You need smooth dependence on initial conditions, parameters, and the next topic also plays an important role. For how long can the solutions be defined? That interval minus a to a. how big can A be? So this is the topic of maximal interval of definition. So what are we, yeah. So the first thing we'll prove that there exists a maximal interval alpha, which is necessarily going to be an open interval, maximal interval alpha beta for solutions of the IVP. So what does maximal mean? I'm going to define it formally. It just means that if the initial condition is fixed, x dot equal to f of x, x0 equal to x naught. So the maximal, maximality refers to the following property. So any solution will be defined on some interval that will necessarily have to contain 0, of course, otherwise this initial condition doesn't make sense. So what we are claiming is if you find any solution of this initial value problem, the interval of definition of such a solution will have to be necessarily contained in this alpha beta, this open interval. So it's a sort of the largest possible. Everything else is contained inside this. If you think about it, it's at first sight, it may look like a completely trivial statement. Of course, there should be a largest possible, but if you think about it, it's not, it requires a little bit of work. Why is it clear? And especially the fact that why should that largest interval be an open interval? Why there should be a largest interval in the first place? And why should it be open? And so we'll prove that. The second thing is, suppose beta less than infinity. It can very well happen that alpha is minus infinity, beta is plus infinity. In other words, the interval is the full real line. But suppose one of them, and here the statement is for beta, but the similar thing holds for alpha. Suppose the right side is less than infinity and x1 equal to limit t going to beta minus x of t, the solution exists. Then so remember this is u and alpha beta is on the real line. X is the solution. So X is mapping this interval into some interval into this open set. The image will look like some curve. Now what we are claiming is that then x1 should necessarily belong to the boundary of u equal to u closure minus u. So if the limit exists, then it should necessarily go to the boundary. This has to do with the maximal property. Otherwise, if it went inside the open set U, if x1, this is x1. If x1 were to lie inside U, then we'll prove that the interval won't be maximal. We will be able to continue the curve solution. So if it was like this, then we'll show that we can actually extend the solution a bit further. So if we want it to be maximal, then x has to be in the boundary. If the other case is if x1 equal to limit x of t going to beta minus exists, and we know that x1 is actually inside U, what I was talking about here, then beta is necessarily infinity. Again, it's a fact that it's maximal. So it can very well happen that the solution, the picture in 3 is the solution sort of wanders off as, but eventually it has a limit point x1. But that's not going to cause a problem to maximality, because in that case it'll turn out that it'll never reach x1. So beta is infinity. It's only asymptotically it's getting closer and closer here. If beta is finite, as in the previous case, then one can show that it will actually reach x1 if x1 is inside the domain. Well, inside or on the boundary, both cases are fine. But if it's inside, it will reach x1 and then you can continue the solution past beta. Here, there's no question of continuing past beta. Beta will be infinity. So it will only asymptotically come closer to this. And there are some examples which will illustrate these various things. So, but let's stop here.